Hey, welcome. Today we're going to talk about spherical coordinates and integration. So we're going to talk about integration, and I'm talking about 3D integration, all right? And we're going to talk about it with spherical coordinates. Let's say, what do we mean by spherical coordinates? So we've probably seen these before. But the idea here is you have a Cartesian point, x, y, z, and you can always express it in terms of three other variables. We'll call rho, theta, and phi. So we have two angles and one distance. So let's write down what we mean by this. So here's our Cartesian coordinate system. And that's z right there. And so we have some point. We'll call it x, y, z. And we put it down there like this. Okay, so that right there represents our theta value. We put a line emanating from the origin to the point itself, and that distance there is going to be the distance rho. Okay, so rho is the distance from the origin, and then we have an angle there that represents where the angle that's in the xy plane. So that's the theta is the angle in the xy plane. And to get the height, we need one more angle. So we have an angle emanating off of the z-axis. So it's phi right there. So let's talk about how to find the transformations between x, y, z and rho, theta, phi. Okay, so first of all, we can get x and y. So what we want to do here is actually kind of revert to polar coordinates. So to get x, we need something that's like r cosine theta, right? So r being this angle here, or this length here. So it's the projected length in the xy plane. Same thing with y. It's the r sine theta as well. So what is r? We're not going to use r in this, but we're going to use it as an intermediary. R is actually going to be the projected length in the xy plane. So we want to think of this angle here. We want to express r in terms of phi, and we can see that. So this right here, that length right there, is sine of phi, and that represents this length right here. So r is actually going to be sine of phi times rho. Okay? Looks good. Okay, so we're going to write that down. Rho sine phi cosine theta, and rho sine phi sine of theta. All right, now we then need to clean up and find z. Well, z is pretty straightforward. It's going to be, z doesn't depend on theta at all. We just want to find out the height above the xy plane, and that's going to be rho cosine phi, right? Rho cosine phi. Okay, so there we go. Those are the transformations between the two, and so the next thing we need to do is then find how to express rho, and that's pretty straightforward. It's just going to be the Pythagorean theorem. Phi squared is equal to x squared plus y squared plus z squared. So that's how we get back and forth between these coordinate systems. All right, so let's talk then again about so when we're doing a three-dimensional integral, a triple integral of some function x, y, z, dv, right? where dV is a small volume element. Okay, so usually, before we've always thought about, we have, oops, we'll draw a better coordinate system there. We think about some region, and we have little bricks, right? So we have a delta y, a delta x, and a delta z. And that creates, and together, those together, delta x, delta y, and delta z, create a delta v. And then when we have some region of the space we want to integrate, and we just have to build out more boxes like that, okay? And we just keep building them out. We keep filling up our space, this volume, with all these boxes, and that's how we compute an integral. But now we're no longer creating little bricks, little square boxes, little cubes. What we're going to be doing is actually taking little elements that are in terms of phi, theta, and rho. So how do we do that? So let's draw another picture here, another Cartesian. Right? So what I want to do then is go, here's my y and there's my z. So what we're going to do then is say, well, what happens when I make a tiny little sweep, delta phi, and a tiny little sweep of angle, delta theta, and a tiny little sweep of angle, delta rho. All right, so I'm going to actually put some numbers down here for this. So let's try to be careful about how we do this. So rho is going to come out like that. I'm going to say that there's a length which I'll call A, and then we'll put another length out here which we'll call B. And so the distance between B minus A is going to be my delta rho, and that's going to be from here to there. Okay. Also, and now I'm going to project this down so we kind of tell where it is in the plane. So I'm going to make a little sweep of an angle alpha. I'm going to make another sweep of an angle, which I'll call beta. And so the difference between delta theta is going to be beta minus alpha. Okay? So that's delta theta. And so we can sweep that out like this. And that makes a little face there. And then finally, we'll make a little sweep of an angle like that. So that makes a little box, I'm going to call it a shard of of a ball or a sphere volume. It's just a little tiny piece. It's sort of like a little wedge of a pie, but it's in 3 dimensions. And so finally that will be right there, delta phi. Okay, so how do we express what these are? So we want to find out a little delta volume. We want to know how to express that in terms of rho, theta, and phi, right? In terms of delta rho, delta theta, and delta phi, actually, right? So we need to find out what that is. So it's pretty straightforward to do. First of all, let's find out what. So we found out what delta rho is. We found out what delta theta is, and delta phi. You can do a similar thing here. We can actually just make that a little tiny angle from C to D. Right? So delta phi is going to be D minus C. Okay. All right, so with all of those put together, we now need to figure out, so this little thing is sort of like a box. it gets pretty close to a box. In fact, it becomes a better and better approximation of an actual cubic box if all of these are getting closer and closer to 0. So what we can do then is actually approximate our little spherical shard of a ball as a box. So that's what we're going to do. So okay, so the depth of this box then is going to be rho, right? So that's the depth of the box like that. And then the sweeping angle across, what's that going to be? Well, it's going to be some little arc of a circle. That's that length right there. So we'll call that the, so that's the depth. And then there's the, which we'll call the height of the box, which is delta phi, but it's times rho, right? So that's going to be the height of the box right there. And that's going to be delta phi times rho because it does depend on how far out you are. So that's going to be, and that's going to be the height. And then finally, to get the width, sorry, I'm gonna do a little erasing there. The width of the box is going to be a little bit more complicated because we need to consider the fact that that width that's being swept across is not going to be proportional to phi, but to something phi times sine of phi. Okay, and then that's times delta theta. So that sweeps across. So the length of this part right there, as it's projected down here, is going to be, that length there is going to be rho times sine phi. Okay, so those put together, so we have a delta V then is going to be, our little volume is going to be, we multiply them all together. So we see there's a rho here and a rho there. That makes a rho squared. We see there's a sine phi. Like that. And then we multiply all the delta phi, delta rho, delta phi, and delta theta together. All right? And so to write them all up, we can say that we're going to integrate over some region, E, and that becomes the same region as before, and now it's going to be F, and then what we put in here is rho sine phi times cosine theta. I'm running out of space, guys, I'm sorry about that. And phi sine, or sorry, rho sine phi sine theta, and then we have rho cosine theta for z, and then we multiply it all by this tiny, call it dv element, which is going to be that right there. So let's do a simple example. So this is spherical coordinates, right? So again, we have our dv is going to be it'll be rho squared sine phi d rho d phi d theta. All right, so now I want to break this up and actually want to do some calculation. So let's try doing a volume. So let's try compute a volume. It's a little pick a shape. We're in spherical coordinates. So naturally, the volume that we should first compute is a sphere. So that seems like the natural choice. So we're gonna, again, to make a volume, a total volume I'll call it, I'm really going to be adding up a bunch of little volumes, which is just going to be triple sum of a bunch of volume approximations, delta V. All right, and that's going to be over a sphere, which I'll just, or sorry, a volume inside of a sphere, so this, I'm going to call it just capital S there. All right, so let's figure out what we need to do to create an iterated integral for this. Well, first of all, and I'll say of radius r. So do we know the formula for that? So we know already the volume was supposed to be, we probably just have this in the back of our calculus book, 4/3 pi r cubed. Okay, so let's figure out what this has to be. All right, so so first of all, we have a sphere, so I'll just write out our sphere right here. So first of all, there's the center of it. So one thing we know, we're going to have to sweep all the way around theta. So theta, so we can write our sphere, S, the set is going to be equal to the points rho, phi, and theta, such that rho is going to vary from 0 all the way to r, right? We know that phi is going to be coming from the very top here, all the way down, all the way to the very bottom. So it's going to be varying from 0 all the way to pi. And finally, theta is going to go all the way from 0 to 2 pi. 0, theta to 2 pi. Right, so that's a sphere defined in spherical coordinates. So that means we can actually make an iterated integral out of this now. So we have v, capital V here, is equal to the integral, and we'll do it from 0 to 2 pi. That's the theta. And we're going to go phi from 0 to pi. All right, and then finally, rho we're going to do from 0 to r, which was the radius of our circle. Okay, and then remember dv was, we're going to replace our dv with all of this. So we're going to have a rho squared sine phi d rho d phi d theta. Okay, so let's compute this now. So we see that one thing we can always do anytime we have a double integral of the form where we have like a f of x and a g of y dx dy, we can always break it up if we have some a and b, c and d. Is always break it up into two pieces, so or two different independent integrals. So that's dx, and then finally integral from c to d, gy dy. And we see it breaks up like that. There's a product of something in terms of only phi and something only of r, and there's actually no theta. So we can do that here, 0 to 2 pi, and we can actually put d theta there. And then we can do the same thing, a product here, 0 to pi of sine phi d phi, and then finally 0 to r of rho squared dr, right? So that again just makes a product of 3 one-dimensional integrals, which is really nice. So this one becomes just 2 pi. That one becomes negative cosine phi evaluated at 0 to pi. And finally, this one becomes rho to the third power over 3. We evaluate it at 0 to r. Okay? So we put that together, 2 pi. And then I put a 3 over there from this 1/3 there, sitting there. And then cosine of pi is negative 1. Negative makes it a positive 1. Minus, so minus a minus 1. Okay? And then finally we have a r cubed. So that's a 1 minus a minus 1 becomes a 2. 2 times 2 makes a 4. 3 pi r cubed, just as desired. Okay, so there you go. That's how you compute spherical coordinates. In the next video, I'll do an example of something a little bit more involved with spherical coordinates.